Hello, everybody. Good morning, UK. Good afternoon, Kazakhstan. Today, hello. Good morning, UK. Good afternoon, Kazakhstan.
Hi.
Welcome to our webinar today's on research and enterprise, organized by Kazakhstani PhD Association of the UK. My name is Asil Bazilgalamova. I'm a country manager for Lavrov University in Central Asia, and I will be moderating today's session. Thank you to all of you for joining today's session. We are waiting for another speaker who will join in soon. Then we'll start. Dear participants, please feel free to submit your questions on our chat box or on Facebook. I think you can start.
Okay.
Hello here. I'm very pleased to welcome you all in today's webinar on research and enterprise, organized by Kazakhstani PhD Association of the UK. My name is Asil Bazilgalamova. I'm a country manager for Lavrov University in Central Asia. Today, I will be moderating today's session. Thank you to all of you for joining today's session. Many of the high-ranked UK universities in UK have very close links with the industry, especially in the area of technology. One of the UK universities, which has an international reputation, is Loughborough. Today, I have the honor to introduce to you our three academics from Loughborough University, whose research is very relevant to the needs of our region. Also, each of our speakers from Loughborough has very strong background and has story to share with you. Also, they will tell their experience and how they built up partnerships with the industry. I would like to brief each of our distinguished guests before they will start their presentations. Our first speaker today, Dr. Alistair Smith, as an expert in the development of sensing technologies which use acoustic emission to identify potential issues with buried structures such as pipelines, dams, and tunnels. He leads on many international research projects in the area of acoustic emissions and has received many awards for his work. Our second speaker, Avinom Barış, is a postgraduate researcher in Loughborough University. Avinom specializes in research into flood risk management. He will join later. Our third speaker, Professor Richard Buswell. He's a senior academic with over 30 years of experience in the area of building systems engineering. He has an international reputation as an expert in the area of 3D concrete printing, which Professor Richard and his team at Loughborough invented around 10 years ago. He's currently leading research into the digital fabrication of concrete using automated methods. I will invite all our participants to submit their questions on our chat box or on Facebook as well. Dear Alistair, I think we can start from you. Are you ready to start?
Yep. Okay. Let me share my. It says host disabled participant screen sharing. Are you able to let me share my screen?
Yes. Just give me a second.
And I think I'll just blank my video while Alistair's giving his presentation, if that's okay. Yeah.
Okay. Can
Yeah.
you all see my presentation
Okay, you
now?
can see. Yeah, excellent. You can start.
Okay. Okay, so hello everyone. My name is Alistair. I'm an academic at Loughborough University in the School of Architecture, Building and Civil Engineering. And my background is in civil engineering. In this talk, I'm going to go through some research we've been doing over a number of years to develop an early warning system for landslides that's based on acoustic emission monitoring, how we've commercialized this system, and the ongoing research that we're doing since the commercialization took place. So first, I'm going to talk about landslides and why they're a problem. I'll then take you through the early warning system that we developed and how we commercialized it. So this is a brief overview of my journey with this research. So I started with my PhD in 2012 on a project called Slope Alarms, and the aim was to develop an early warning system for landslides that uses acoustic emission, and I'll explain what acoustic emission is in a moment. And then my postdoc research from 2015 to 2017 focused on redesigning the landslide early warning system for low-cost manufacture. And the aim was to develop a system that could be used by vulnerable communities in low and middle-income countries, because these are the places where lots of people are killed from landslides. And early warning systems would be able to reduce these fatalities, but they're currently too expensive. And then it was in 2017 when we commercialized the landslide early warning systems. And since then, alongside the commercialization, I've been working on developing new acoustic emission technologies for new applications, such as for buried pipelines, for pile foundations, for dams and retaining structures. So landslides kill thousands of people each year. This map, each black dot on this map shows the location of a landslide that resulted in fatalities between 2004 and 2010. And there were 32,000 fatalities from landslides in this period. And this is focusing specifically on landslides that didn't result from earthquakes, because they result in lots of fatalities, but the mechanisms of the landslide are very different. And you'll notice that there's lots of clustering of these black dots. So the landslide problem is clustered in specific areas, and there's reasons for this. First of all, the topographical relief, as in steep terrain on which slopes can form and fail. The frequency and magnitude of precipitation, so rainfall, and how that enters the slopes and increases what's called pore water pressures, which results in failure, and the population density, so the likelihood of the landslide interacting with people. And these are a few photographs just to highlight the scale of the problem. So acoustic emission are essentially high frequency noise, and all materials generate acoustic emission when they are stressed or they deform. And the ground is made up of lots of small particles called soil. And when deformation takes place, these particles interact and they release high frequency noise. And our research aims to listen to this high frequency noise to develop an understanding of what's happening inside the ground. So the idea is that if we're listening to high frequency noise that's increasing in frequency and magnitude, then this would indicate some failure processes taking place. This is the system that we developed for slopes. So it uses what's called an active waveguide. So you'll see here, this is a cross-section illustration of a slope, and we drill a hole that intersects any potential or existing shear surface in the slope, and a shear surface forms when a landslide takes place. And inside the hole, we install a steel tube, which is the waveguide, and around the steel tube, we backfill with granular material. At the top of the instrumentation, there's all the electronics, so the processing unit and the early warning system, which is protected by a surface cover. Now, when the slope or the landslide moves, it causes the backfill around the steel tube to deform, and this generates high frequency noise, which propagates up the steel tube to the sensor at the ground surface. So that's how the system operates. In terms of the early warning system, so we've just talked about the active waveguide, and that's the part of the system that generates the acoustic emission, the high frequency noise. And that propagates up the steel tube to a sensor. A transducer is a type of sensor at the ground surface. And the sensor converts the mechanical vibrations to an electrical signal, which are then processed by the slope alarms sensor unit. And it does this continuously and in real time, and it's counting the energy that's released in the acoustic energy. And we set a series of trigger thresholds. And when these trigger thresholds are exceeded, the system communicates this with a communication node via a wireless network, which then sends text messages to responsible persons to take relevant action, which could be to evacuate, or it could be to stop traffic entering part of a rail network or a road, for example. Community Slope Safe is a low-cost version of the system, and the principle is that we reduced the functionality. So this system doesn't send text messages. Instead, it has an audible and visual alarm, and the base station is located with a responsible person within a vulnerable community. And when the alarm is triggered, the siren goes off, the flashing light goes off. The idea is that they then implement the emergency procedure. A lot of the work that we've been doing over the last 5 to 10 years on the project has been developing proof of concept and progressing the research through what's called technology readiness levels. So when you develop an idea and you start to formulate the concepts, the technology readiness levels that you would be operating at are TRL 1 and 2. But then when you start to demonstrate how it works in the lab, and then in the real field environment, you progress through TRL levels. And this process is a really important part of commercialization. So we developed the process and demonstrated it in the lab, and then we embarked on lots of field trials around the world. So that resulted in 28 sensors being installed on 15 different slopes in 6 different countries. So we have a big evidence base of the performance of the system, which was really valuable when we were talking to commercial partners and demonstrating that the system works. So these are some of the sites that we have in the UK, or we operated in the UK. Some of these are purely research sites, but others are with stakeholders and industry partners, such as Network Rail, the Environment Agency, and local councils. The slopes are all different. Some are adjacent to a railway, some are flood embankments, some are coastal slopes, which are impacting on road networks and housing developments. These are some of our international sites. So we have 2 sites in Canada, one with Alberta Transportation, which is a landslide impacting on a highway. And then we have a site with both Canadian railway companies in British Columbia. We have a site in Austria with the Austrian Railway, and a site in Italy, in the Eastern Italian Alps, with the Italian Research Council. And we have 2 trials of the community slope safe system, one in Malaysia and one in Myanmar. This is the system that RST Instruments developed, commercialized based on our research. So after we completed lots of field trials and we built up an evidence base, we investigated how we would like to commercialize the system. One option was to set up a spin-out company and run our own business, but we didn't want to do that because we wanted to continue being academics and doing research. So the route that we took was licensing. So we were looking for a commercial partner, and we started to speak with RST Instruments, who are a worldwide distributor and manufacturer of geotechnical instrumentation. and they're based in Vancouver. In 2017, we went to the head office and we pitched the idea to them and demonstrated all of the evidence that we have. And then we embarked on a negotiations for the licensing agreement, which took several months. And then after we agreed the license, RST developed their own version of our slope alarms and community slope safe systems. And they've called it the Geoacoustic Aware, the GAA, and that's what you can see on the screen now. This is available, it's being distributed around the world, it's on sale, so if you want one, you can go and buy one. So just to provide an overview of the journey, so slope alarms and community slope safe are the research sensors that we've developed for landslide early warning to demonstrate the concept. And these have been commercialized by RST Instruments, and they've developed their own versions of the sensor, which are on sale now. Alongside the commercialization of the landslide early warning system, we're now developing acoustic emission technologies for new applications, such as to detect deterioration or failure processes in buried pipes, pile foundations, retaining structures, dams, etc. And I just wanted to show you an example illustration how the listening to infrastructure concept works. So here there's a buried pipeline which is being impacted on by differential ground movement. The differential ground movement is causing the soil around the pipe to move and deform, which generates the high frequency noise, the acoustic emission, which propagates along the steel tube as guided waves. And then we listen to this with distributed sensors. We can locate where the sound is coming from, and we can provide an early warning for decision makers to take action. There's lots of acknowledgements because we couldn't have done any of this work in isolation, lots of collaborators and stakeholders. Thank you very much for listening.
Thank you very much, Dr. Alistair, for your excellent presentation. Let's move to our second speaker, Dr. Avi. Hello, hello.
Hello.
Yeah. Are you ready? Are you happy to continue?
Yeah, I can present, if that's okay.
Yes. Yes.
Hello. So everyone, I'm Avi. I'm the co-founder of Pre-Visico. We're a flood forecasting company that spun out of Loughborough University in January 2019 to reduce the cost of flooding globally. I did my PhD at Loughborough University, supervised by Professor Yu, who is an expert in hydraulic modeling. And he developed his own software for modeling flooding over 20 years ago. And over the years, he's been publishing it widely. But since 2016, he's been working on a flood forecasting system in partnership with the UK government, who realized that there's a big gap in the existing warnings that are available to members of the public. And that project kind of snowballed into a very large one where we were really working hand in hand with the government. And we realized that to really operationalize the system and to kind of provide warnings to a far wider market than just government, we needed to form a spin-out company. Our mission as a company is to really make scenes like this a thing of the past. Across the globe, too often things that shouldn't be lost due to flooding are. And a great example of this is cars, because you can always move a car to higher ground. And if you have advanced warning, there's a lot of actions that you can take, especially from your property, moving kind of sofas or TVs to upstairs, or your insurance documents. There's or all sorts of different kind of actions that can be taken both from a homeowner but also from a business. So the cost of flooding is rising very rapidly. It currently stands at $90 billion a year and is expected to rise to well over $1 trillion by 2050. This is due to climate change and urbanization. So this issue is only going to get worse. And in particular, because the climate is getting more volatile, sort of flash flood events are going to occur more frequently. So to really reduce flood risk, you really need to take three main steps. You need a flood action plan, so you know what you need to do when the flood hits. You need to have some sort of flood defenses if possible. and you need to have an actionable warning. And when you have an actionable warning, they have very big returns on investment. So this is where the EU early warning system for river flooding, for every €1 they invested in the scheme, they returned 100 or 400 back. And here is the sort of warnings we can get in the UK, but again, across the globe, similar levels of warnings are available in different areas. And the map on the left is for rivers and sea provided by the Environment Agency. These are really useful and they help millions of people across the country avoid flooding every year. But the problem with them is they're only available for large river systems and the sea, so that's under 2.4 million properties. They're not available for small river systems, and they're not available for surface water flooding, which is the biggest flood risk in the UK, but also globally. And I think the people often overlook surface water flooding because it just comes and goes very quickly, and it's rarely on the news. But just for those of you who are not aware of what surface water flooding is, it's when there's a big, heavy downpour of rain and there's flooding that doesn't actually come from a river. So it could come from happen in a car park or along a road. That's just because the current drainage system can't handle the capacity. Same problem in the US. This is the sort of warnings that they have available to them. So with the Professor Yu's flood modeling software, we developed a technique to remodel flooding every 3 hours, and we formed a partnership with IBM's weather company, where we take their rainfall forecasts and predict what the flood will look like for the next 2 days every 3 hours. So what we ended up producing was a depth, extent, and a time that the flood would hit, and we produced it right at the property level. And we've now scaled up to a UK-wide, but we've also got pilots across the globe in the US, in Japan, in Australia. So our visualization platform, we were live in November. So the UK was hit by flooding in November, and we were live for that event. So here's kind of a little visualization of what our warnings look like. So we provided an hour-by-hour prediction showing right down to the street level which areas would be hit and which districts would be worst affected. And you can really zoom in and see right down at the street level. So maybe I'll fast forward through this video. You can see right down, you can see individual properties, when the flood will hit, how deep it will be, and what the surrounding roads will be, which surrounding roads will be affected. And I think, as I kind of said earlier, there's a lot of data goes into it, from the land cover, geology, elevation, and we're in partnership with IBM for the rainfall. So we will set it up anywhere, so it can be set up anywhere across the globe. All we need is to access the data, to then model, inspect its performance, to calibrate it. And then we've also, in partnership with Leicester University, we've developed a satellite image detection algorithm that then detects flooding from satellites, which combines with our forecast to then be able to show what actually then was hit by flooding. And again, the Cabinet Office in the UK, so that's the central government, they launched the platform in partnership with Loughborough University and Previsco last week, where they have 4 cities, so London, Manchester, Birmingham, and Leicester, all trialing the service. But for our core customers, they can get it across the whole of the UK. And the Cabinet Office, again, they use it really to coordinate their emergency response, so to send police, fire and rescue to the right locations before the event hits. And they've been using it for that purpose. But as a company, we're not just targeting government, we're also working a lot with insurance companies. And where we're really working with insurance companies is helping them better support their customers. So for example, telling them that you're going to be hit by flooding at 3 p.m. today, and it will be about 25 centimeters. Maybe move your cars to high ground, maybe set up some defenses for your property. It can also, for the claims and operations teams, sending people to the right locations to really reduce the losses is where we then also help. And we also then have a data feed that people can use for all sorts of different purposes. And really where we want to be heading is we want flood insurance to be lower, and it should be lower if people are better at managing their risks and reducing the sort of losses that can occur. then the insurance can be reduced, and it can be a far better relationship. So that's really as a company where we're heading. So thank you very much for listening. I'm happy to answer any questions.
Thank you very much, dear Avi. Dear participants, if you have any questions, please submit your questions on our chat box or on Facebook. Later, at the end of the presentation, we'll have some time to discussion. Thank you.
Okay, thanks.
Professor Richard.
Hello.
I'm
Yeah.
happy to continue. Over to you.
Okay. Let me just get to grips with the technology. I think that's on there. So if okay, can everybody see that?
You can see. Excellent. Yeah. Thank you very much.
Yeah. Okay. Thank you very much for the opportunity to share this bit of research with you today. I've been involved for the past 15 years or so in developing a technology called 3D concrete printing, which you may have heard about, and there's been lots of media, lots of interest in recent years in the space. So I'll give you a little bit of an overview of background, the sort of work we did, and the sort of research challenges that we're currently exploring. So the construction industry worldwide, it has different issues in different regions, but generally we have a lot of common problems. Quality and project overrun issues are a constant issue, particularly in the UK. Hazardous working environments, we want to take people away from harmful environments. Key shortages in skilled labour are also a problem. And in places like the UK, we're looking towards large investment in infrastructure and to constantly improve the built environment. So with these problems also comes the pressures of improving our built environment. As part of this, we know that automation is going to be key. We have to increase productivity, increase the quality issues, but at the same time reduce the cost of delivery. And automation has been demonstrated in manufacturing to be a way of doing that. And there's a lot of interest, both with applying automation to on-site operations, but also in particular making most use of off-site manufacturing. So this is where we're building sections of buildings or parts of buildings or volumetric chunks of buildings in the factory under tightly controlled conditions, where we can generate better quality and have a more production control, produce things at the right time so that when they arrive on site, it's much quicker to install on site and reduces the site time. One of the key issues there is that if we can sequence the on-site occurrences, on-site events in a better way, we can reduce the overall time for construction on site, and that's where the real big cost savings are. But in order to do that, we've got to be able to manufacture on demand, deliver on demand, and have components that fit into their places at the right time, rather than having to have a piece and having to rework it, where a lot of time is lost in the traditional handcrafted industries that we've got. So, and also to orchestrate this, you are having to move to digital platforms to look at the way parts are manufactured, call-offs, data, positioning of those parts, etc. So there's a big increase in the interest in digital modelling and BIM to support this. I've been very interested in looking at digital fabrication with concrete. So that's where we can use the same digital information contained in those models to control the manufacturing process itself. And if we can have a digitally controlled automated manufacturing process, you get other benefits such as, you know, tighter production control, more repeatable quality, and higher productivity. There's been a whole bunch of great work done internationally over the last probably 15, maybe 20 years. There are just a few of those on the screen now. You've only got to Google to see what people are doing. But this is everything, where we're applying a shotcrete, sprayed concrete approach in an additive way to generate interesting forms and have freedom of shape and design, using extrusion in a controlled way, micro slip forming, as well as creating formworks in a digital way so we can cast conventionally. All of these things have their place and their advantage, and in fact some of the flexible mold approach at the bottom there, this is a technology that's been developed and is now being used to deliver the Q8 airport building. So these technologies are genuinely finding their way out into industry and are answering big industrial questions, which makes it a very exciting area to be engaged in. As for growth,
sorry, Professor Richard.
Yes.
I apologize, but you can't see your presentation. Your presentation is not moving, actually.
Okay, can you see? What can you see?
You can see first page only.
Oh, the first page only. Okay. In that case, let me exit that mode. Can you see this?
Yes, you can see now. Yeah.
You can see that. Okay. Right. No problem. I shall continue from here. Okay, so apologies for the technology blip. So digital fabrication has been growing at a very rapid rate. So there was some initial work done by a chap called Joe Pena in 1997, but really the first additive manufacturing occurred in the mid-2000s, and we were one of the first three institutions, if you like, organizations to look into additive manufacturing. There's contour crafting in the US, which you may know, where you had an automated method of building a wall in situ on site. There's a process called D-Shape or Monolite in Italy, which is a very, very large 3D printer that uses sand and a binder. But we were interested in whether we could use extruded concrete in an additive manufacturing way to produce parts that were as good as cast. Those initial bits of work has set off over the recent years a vast number of organizations looking into it, and now there's over 30 commercial offerings for these digital fabrication technologies and additive manufacturing in particular. So it's something that is not only of great research interest, but is also of great commercial interest, and there's many startup SMEs in this space doing work. Loughborough, the work that we developed here also span out a startup company that is also looking at delivering additively manufactured products and also processes and machines to for others to deliver the same technology. Okay, a little bit of our history, if you like. So we developed 3D concrete printing. This is a technology that uses a three-dimensional CAD model of an object. We then slice it into a number of virtual layers, and then we trace out all of the solid material, as you can see in that middle image, with a filament of concrete, and we generate a tool path. We then print the concrete to generate a solid object, which you can see at the bottom here. And this was the bench that we originally started with. It's very the same as additive manufacturing, but just on a larger scale with concrete. This was the first component that we printed, and it was a world's first additively manufactured 3D concrete printed component. It was also the first to be manufactured with reinforcement. We then looked at different products and where we might be able to deploy the technology. And panels is an interesting one because it is expensive to manufacture with molds. So the thing with additive manufacturing is you're trying to create a freedom of geometry and component without requiring a mold, because the mold is quite expensive, and the more complicated the geometry, the more expensive the mold gets. So if you're able to employ these processes to give you more freedom of design, freedom of form, then you can add value by having bespoke or very low volume manufactured components. And in actual fact, in construction, what we've done over the years is to try to modularize that, like the brick in a wall, for example. It's a repeatable, same size component, but to yield more benefits, to get more perhaps environmentally responsive buildings, and to give a more architectural signature to buildings, having freedom of shape and form is of value. So we focused on generating these panels. These were the world's first doubly curved panels. They're conformally printed. They're also hollow. So this was concept parts that were sort of demonstrating the flexibility that could be afforded by the process. This was all completed. Those projects were done in sort of about 10 years ago. And so on to more current research. We're still very much active in the field. We have 2 research projects at the moment. And we are interested in things like the materials. So we extrude the concrete material. We have to understand the rheology. We ask it to do a lot. It has to be thin and pumpable to come out of the nozzle, but then it has to stay in place. So this has its challenges because cements and aggregates are manufactured and natural ingredients, and this affects the rheology quite a lot. So understanding the control, the admixtures, the way we can test is still very much a research question, but one that is absolutely key to understanding in order to get these processes commercial and in order to have them being as effective as they can and as cost effective as they can. The hardened properties are also critical. We're building concrete components, and at the moment the technology is such that we can manufacture quite safely things like benches and seats, which are large volumes of material. We have freedom of form, so we can design them in very cool and sexy sort of ways, but they sort of sit in compression. There's no real structural load on those components, which makes them a very good first market product. However, if we want to do more exciting things, structural things, cladding panels, then we have to understand far more about the mechanical properties of the materials such that we can actually do structural design, which is not only the matrix material, but incorporating reinforcement. And so we are undertaking work on characterizing reinforced concrete materials right at this moment. Additive manufacturing means that we are able to have freedom of design, but of course we don't have complete freedom of design. We're still stuck with gravity as we're trying to build components up. The material rheology has limitations. We can't build in thin air. So there are certain constraints that go hand in hand with manufacturing these products. So the design of the parts has a large part to play in a successful part. And so understanding the design and how we translate that into process control is also a very hot topic. And again, there are new companies now finding niches where they're developing software specifically to service this new market. Finish, assembly and function. So what do we use the parts for? Can we actually add value to the part, not only in an aesthetic sense, but by having more functions in there? And one of those we tried at Loughborough was perhaps an acoustic panel to do some sound absorption, maybe using a Helmholtz approach, but also recognizing that these parts are largely going to be assemblies. And so if they're going to be assemblies as they are in buildings, you know, we make buildings, we don't make them out of monolithic panels. They're usually sections of panels that are fitted together in a certain way. That fits very much with an off-site manufacturing approach, but we have to understand how we can make these panels to be assembled together, how they can fit together, etc. So all of these are helping to inform the design and the production and post-production assembly of components, which is also interesting. In order to assemble parts and to have them to be aesthetically as good as they can be, we have to understand the conformity. So how accurately can we actually print the materials? And again, a lot of the products that are out there at the moment, like benches and planters, are the actual tolerances of those manufacturers are not that critical, and they're sort of exotic parts that have a certain kudos on their own. But if we want to move that again into components that fit into construction, we have to be able to assemble to far tighter tolerances. And so we're quite interested in how we can enhance current 3D printing methods to produce those sorts of tolerances in our manufactured parts in an automated way. As part of that, we also have to adopt new ways of measuring components, and we're looking to the manufacturing sector to look at how we can interrogate manufactured components to learn more about process capabilities and how they fit in. So I guess just to sort of wrap up, we've set up a startup initiative. So we've done some research. We invented the technology some years ago. We are undertaking current research with industrial partners now to improve the technology, but we've also set up a startup initiative to try to bring the technology into the sector. And that startup is embedded in a precast organization where we can learn how to industrialize the process to deliver cost-effective parts. We want to be able to deliver greater design freedom in objects. We want to increase the productivity of a manufacturing environment. We want to make that environment safer for operatives. And we want to generate greater flexibility in manufacture. So this is not only in the shape of the part, but in actual scheduling the production to move us towards a time when we are far more confident about how long it will take a component to be made and hence shipped. And the other exciting thing about using robotics to enable the 3D concrete printing is that we're able to build very flexible manufacturing cells that can produce a range of components. So we're able to shrink traditional factory footprints to a much smaller area, which is also commercially an advantage. So I think what I'd like to wrap up is just to say that the whole digital fabrication area, and particularly 3D concrete printing, is a very live area. It's very exciting. It's one of the few times, and probably the only time in my career, where we've had cutting edge research literally running in parallel with cutting edge commercialization initiatives. You can find these all over the world. I would just like to say, if anybody's really interested in finding more, then please Google Digital Concrete 2020, which is an online conference run out of Eindhoven. And it runs, starts, I think, on the first week in July. It's an afternoon run session. It's quite reasonable because it's an afternoon run session, but there you will have all of the latest cutting edge research in this field. And it will be a really interesting conference for those of you with a particular interest. So with that, I would just like to say thank you very much for listening to my presentation. If you're interested in research at all, then please contact me. But also, if you are interested in getting involved in manufacturing with 3D concrete printing, or if you are a research institute looking to sort of have some equipment in order to undertake some research, then again, please contact me. We've got a startup initiative which is capable of supplying equipment to people who are interested. So my email's at the bottom. Please make a note of that, and thank you very much.
Yeah, Professor Richard, thank you very much for your excellent presentation. I think you covered everything. Now we have a lot of questions coming from our participants. Dear participants, please feel free to submit your questions on our chat box on Facebook as well. I think I will start ask questions. First question, I think I will ask from, the question is, can you please share about university practices to launch a spin-off? How did you know what your project idea is commercialized? is there opportunities at Loughborough to test the idea of commercialization? I think the question's to Dr. Alistair.
Okay, I don't know if Richard is better placed, having done a spin out.
Can you answer this question?
Well, perhaps maybe I'll comment on Alistair. I think the interesting thing here is that there is more than one option to commercialize your IP, and there are a number of avenues to take. And you either sort of go down a consultancy route where your expertise is available, where people can hire and get access to that expertise. I think the one that universities perhaps traditionally, I know Loughborough has been interested in, is licensing, which is the example that Alistair showed, where you can develop a new technology, and then it's more about finding an agreement about how organisations can use that IP, and that's quite good for universities, because it means that when you try to exploit IP, particularly when there's patents involved, and these are expensive. We can't patent and protect all ideas, and so we have to back certain ones. And where you have a good idea, where there is a commercial organisation that's interested in taking that to market, then a licensing arrangement can work very well, because it means that they can do a deal with the university gets some income, and that supports the IP patent, and the company can go ahead and make some, and there can be some very nice partnerships. And Analysis was one of those, which is a super example of where that worked really, really well. Setting up a spin out is different. And my experience is that there's got to be an appetite to do it from those involved. It's not an easy track at all. What made it happen for us is that we had a couple of PhD students who were working in the area, but they were less interested in an academic career, and they were very keen on business and commercialization. So they were the seed, if you like, that said, we want to go and make this happen. And then there was a little bit of serendipity in that we found a precaster who was really interested in the possibility of digitizing the manufacturing process and automation and moving forward, and recognize the problems that they were having with labor. And so in a perfect storm, these things came together, and we were able to set up a little initiative to take that forward. So I think with them, they're very different organisations. The university is quite keen on backing either, and it depends really on the case and how strong that is. Alistair, I don't know if you have anything to add?
Yeah, I just wanted to add that I think part of the question asked what support we have at Loughborough for these sorts of things, and we have an enterprise office, and they're key to helping us identify which opportunities have commercial prospects. They're always involved in establishing partnerships, negotiating contracts, developing commercial strategies. So we have a dedicated team that helps us with all of these things, which is really valuable. I think so. For example, with the licensing agreement that we spent several months negotiating and revising, we had a dedicated IP member of the enterprise office working with us, because we would have found it challenging otherwise. So we have a support structure that helps us with everything that we're doing.
Absolutely.
Yeah, thank you very much for your detailed answer for both of you. And I think the second question, I think I can ask the question to Avi, Dr. Avi. Satellite technology monitor flooding. Can you please share more detailed information how satellites help to monitor or forecast flooding? Dr. Avi.
Yes, so the forecasting is done from our side. So we will use a lot of data about kind of the geology, the elevation, and the weather forecast to be able to predict the flooding for the next 2 days. The satellite imagery then comes in as soon as it's then happened. So there's Sentinel, there's different types of satellite imagery. that provide a radar and optical images of the land, and those are available immediately after the event has hit. So we've developed automated processing to analyze that imagery and integrate it into our modeling to then be able to produce a map of what the flood looked like. So it's really based on kind of the SAR technologies and the kind of established algorithms for monitoring that.
Yeah. Okay. Thank you. Thank you very much. I think
You're frozen.
Ooh,
increase it
but,
in that way. Thank you.
sorry, I think you got cut off. I didn't hear you just then.
Yeah, I think you froze on my
If the
screen.
question is clear, or I can ask it again. Or
Please, could you ask it again? You cut out, so I couldn't hear you.
Dr. Alistair, I think you unmuted.
He said that you cut out when you asked the question. Your video stopped, so we didn't hear it. Could you repeat? Could you repeat the question, please?
Professor Richard, we can hear you.
You right?
Can you hear me? Can you hear me, Richard?
I can. Yes.
Okay, I can hear you.
Yeah. Can you hear us? Can you hear us? So I think we have a communication.
Avi, can you hear
I
us?
apologize for technical
I can hear you
issues,
fine.
but
Yeah. So I think the three of us can hear each other. Can you hear us?
I'll type a message.
Okay.
Right, you all froze there for a moment for me.
can you hear me?
Yes.
Yeah, now?
Yes.
Okay, okay, let's move. I apologize for technical issues. Let's move for another question. I think next question I will again address to Professor Richard.
Okay.
Do you accept interns from your group, local PhD students in Kazakhstan who want to come to the UK for 3 months or for 1 year?
We would have a look at a case, and if it made good sense for the student and their studies, and it fitted in with the work that we were undertaking, then we would consider that. Yes. I hope you heard.
I heard.
Yeah. Did you hear my response? No.
I'm going to have to shoot off, so thank you very much, everyone.
Okay.
Okay. Bye-bye, Avi.
Bye.
Thanks. Right, I think I'm going to, let me just, why don't we, I'm thinking,
I apologize for technical issues because I can't hear Professor Richard, all of you.
no, yeah. Yeah, so I've just chatted, Alistair. I don't know. we can hear, but just sort of
I
said
can
that
hear you. Okay, I will
okay, yeah,
continue.
it's very intermittent.
I apologize for
Yeah, well, we
technical
understand
issues,
there's nothing you can
okay,
do.
I will ask the next question. I will move for next question. Okay.
Okay.
What is the computation of concrete? Is there any way research doing on the utilize mining waste in printing 3D concrete?
So, can you hear me?
I think we just continue.
Okay. Yeah, okay. Okay. Hopefully people will hear. So the big issue with concrete printing in terms of the materials is getting a material that will print and do what you need it to do. But as a result of that, commonly very high cement content materials are used, which is not, which if we could reduce that, it would reduce the CO2 impact of the mortars that we use. So using different materials is something, new formulations is something that is of interest. But making them printable is a technical problem and one for research.
Thank you very much for your answer. There is another question. Are you interested to collaborate with Kazakhstani mining industry?
We would be happy to have a conversation, and if there was if someone is interested in talking to us, then we would be happy to have a conversation, of course. Did you hear?
I think the chat is saying that they can hear you.
Okay. Okay. Okay, that's good. We hear you. Okay. So it seems that the people listening can hear okay, and it seems that our communication is a little broken.
Okay, thank you very much for your answer. Dear participants, please feel free to submit your questions on our chat box or on Facebook.
So may I ask a question of Alistair?
Go on.
If we're waiting.
Yeah, go for it.
I was just really curious. I thought your presentation was great.
Thanks.
And what, with your slope sensor, what sort of radius is one sensor able to listen to?
So it listens literally just to the borehole, the hole in the ground.
Okay.
So it's because it's such high frequency that it's listening to, the waves attenuate very rapidly.
Mm.
So it can't monitor a large volume. There are techniques that you can use to monitor a large volume, which monitor low frequency, sort of microseismic noise, but low frequency. But the problem with them is that you get lots of background noise and false alarms because environmental noise is low frequency.
Yeah. Okay.
So we really wanted to make sure it was high frequency to filter out the background noise to minimize false alarms, but that restricts the volume that you can monitor, which is again why we use the steel tube, so that we can penetrate to the depth where displacements are happening, to pick up the process.
And then key for the system is to make sure that you have these located in the right places.
Absolutely. So all instrumentation projects, geotechnical engineers would be involved in trying to understand what the likely mechanism is, and then deciding where to locate the instruments. And that's the same for all instruments, including ours.
Yeah, no, really interesting. And how deep is the borehole? I'm sure it was on your slide, but
So it varies. So each landslide is different. So when the geotechnical engineer has to decide what the mechanism is or understand it, they would have to predict or measure where the shear surface is going to be, and you have to try and penetrate the shear surface. So some of our slopes that can be 1.5 meters deep. On another one of our slopes is 20 meters deep. Right. And we have one that's installed 43 meters deep.
Wow.
So they vary in size quite significantly.
Yeah. Okay. Really. Yeah. Yeah. So part of the process is actually doing an analysis of the slope and understanding where it's likely to slip it.
Absolutely.
Yeah.
Yeah, that's very key.
Okay. I don't know if everyone has seen that. We seem to have lost our host temporarily.
I think maybe they're. Oh, I think our host is trying to reconnect, maybe to get sound.
Okay.
Dear speakers, sorry, we have some technical problems. Asel just disappeared. I don't know, some issues with her sound. So let's check once more our questions.
Can you hear us?
Yes, I hear you perfectly.
Okay, good.
Yeah, you're very clear for us as well.
I think she has some issues.
Yeah.
That's fine. So dear Richard, I think you had a question about mining, right? Mining waste.
Yes, I think we did that one.
Yeah, I think we did that one.
Okay, that is great. Dear Richard, did you have a question about digitalization?
I don't know if you've done that one yet.
I don't know if I've done that one.
So you mentioned like about digital automation. So can you please share more about digital automation? What kind of software programs were used and how the efficiency of your work increased and in what way?
Okay, yeah, that's good. So I think so I think the benefits of digitalization, I think everybody can see. You know, if we had fully digitized models of buildings that would be able to model all of the components, so we could send that information sort of directly into manufacturing processes, so we can order just in time. You can imagine a car being assembled, and the way cars are assembled is that all of those components that make up that car are manufactured in factories all over the world, and they are all couriered in by people like DHL literally within 2 hours of being fitted onto the car. So there's no storage. It's all literally just in time. And as that car's moving down, the body panels are coming in and they're being installed. And you can imagine how that level of automation with the building could yield tremendous benefit. But we are some way away from that. And of course, buildings are not the same as cars. So we're always going to have, I think, some handcraft. The question is looking at which components we can automate and where digitization can help. With our specific process, we use fairly standard 3D modeling tools to model the components, like Rhino or other 3D modeling software. Then what you have to do is take that model and convert it into G-code or a computer numeric controller, a CNC toolpath that is able to control the machine and tell it where to print. And that can be done in a number of ways. If you are building in horizontal flat layers, as most processes, then you can use freely available slicing software that has been used in the additive manufacturing world for many years. So you can download free software, generate toolpaths for, and fused deposition modeling is the plastic modeling that uses a thermoplastic extrusion. The process is very similar in concrete printing. So we've used those models and we still do. Where you want more control over where you place the filament, and when you start looking into the mechanics of how these processes work, that has some advantage. Then a lot of people are interested and have used Grasshopper, which is a plugin for Rhino, which allows you to do sort of parametric modeling. And there's many groups in the world that use those. At the moment, we are looking at using PowerMill in Autodesk, which also has an additive manufacturing module that they've developed to that, and we're exploring that at the moment. So there are various ways of doing this. There are certain nuances with concrete printing. So there are companies like HAL Robotics who have specialized in generating software for 3D concrete printing, and their software powers a lot of the X3 processes. And there are others coming into the market, like RapCam is another one, where they're looking at developing software specifically for the application. So there are lots of things off the shelf that you can use, but they all basically use a 3D model, a way of generating the tool paths that generates G code normally, and then there will be some conversion from that G code into the machine language, whatever that is. And it might be G code, but it could also be a robot language if you're using robotics as your positioning tool. There is a lot of work to be done to make this seamless, lots of research, but again, there's also commercial interest. So it's an exciting area to be involved in.
Thank you very much. Yeah, thank you. I apologize for any connection.
It's fine. No problem from here. Fully understand.
Dear participants, please submit your questions on our chat box and on Facebook as well. I have another question to Dr. Avi. Then Almaty is also located in the area which is at risk of earthquake in respect of new building construction or predicting earthquake before they happen. How prepared is Kazakhstan in your opinion? Dr. Alistair, I think I can address this question to you.
You could. I think Avi has left. He had to go. I don't have any expertise in earthquake prediction, I'm afraid. So earthquakes cause landslides through a process called liquefaction, where the seismic activity causes the pore water pressures in the ground to increase, which causes landslides. But the earthquake and the seismic activity is not an area of my expertise. I would not be able to confidently give a response to that question, I'm afraid.
Is it fair to say, Alistair? May I just on that? Obviously, an earthquake might trigger a landslide, but also other natural events might also cause landslides, isn't it? Is that right? So you're really triggering on something that causes a landslide, not necessarily if it's because of an earthquake. Absolutely.
So the landslides are caused by various different triggers. Earthquakes or seismic activity is one trigger. Maybe the most common trigger is just rainfall. So in the wet months in a region throughout every year, the water pressures in the ground increase because there's more precipitation, and that causes the strength of the ground to reduce, and that's what causes failures. So I guess they're the two main triggers of landslides.
Okay. Okay. Thank you very much. Okay, I think we have last question to all of our panelists. One of the 1st of May this year, there was a big dam collapse in Uzbekistan. It caused huge damage to environment, and more than 70,000 people were displaced. The dam was only 3 years old. I would like to ask each of our panel members how their area of research could help to prevent such disaster in the future. Actually, a lot of people from Kazakhstan suffered from that as well.
Okay, so I guess the two angles to answer that question. One is the early warning approach to detect when the failure is about to happen, or the integrity of the structure, so the monitoring. And the other is the quality control and the design, which maybe Richard probably, I don't know if it was a concrete dam or an earth dam, but from my perspective, after the dam was constructed, it would have been based on a design that likely would have been designed against a serviceability limit state failure and an ultimate limit state failure, where displacements would have been predicted. So if instrumentation was installed during construction, these measurements could have been used to compare the actual performance of the dam with what it was designed to do. And that would have allowed you to assess the quality of the build and whether it's less stable than it was designed to be, for example. And then continuous monitoring, for example, every hour, every day, to detect any displacements would have been valuable in providing an early warning of the failure process. So that's my angle from a monitoring and instrumentation perspective.
Yeah, and I think from a manufacturing technology perspective, I think one of the one of the interesting drivers that's not necessarily concrete printing, but is in automating the in situ placement of materials, is that, of course, we might get to a point where we don't have to put people in dangerous places. And you know, if we dig a hole or a trench for a foundation, it becomes a dangerous place for people to be in because the ground can slip, people can be harmed. And so if we're able to do those sorts of operations in an automated way, then it's possible we remove people from those situations. So in the dam case, maybe if we have data from the monitoring system, we're able to model perhaps how to affect repairs on that dam, if we can predict what might happen, and maybe automation technology may be able to help in affecting those repairs, perhaps without people actually being in harm's way themselves.
Okay, yeah, thank you very much. It was our last question, I think. If you don't have any question, I think we can approaching the end and we can finish today's webinar. I would like to thank all our speakers for excellent presentation, interesting and excellent presentation, and our Kazakhstani Association for organizing this webinar. Thank you very much for your time, for joining today's webinar, and please stay safe and see you soon. Thank you very much.
Thank you very much for the invitation. It's been great.
Thank you. Thank you for inviting us.
Bye.
Bye-bye.
Bye.